Hello everybody, my name is Austin Striegel. I work at Western Digital and my team handles the HDD codec design for basically our hard disk drives today. So my team, along with other folks, I'd like to really recognize Yuri, Rick, and Naranje from my team. They've been participating for the last couple of years here as we've been exploring, looking into basically how we can apply some of what we already do today on magnetic storage to the DNA space. Okay, so what I'd like to kind of overview for everybody today is, I know not everybody is going to be familiar with basically HDDs or hard disk drives, so I have to at least spend a little bit of my time trying to explain how magnetic storage works. I won't go into all the details because that would take much longer than the 15 minutes I have. Then I'd like to kind of go through one of the operations that we apply to HDDs today is soft decoded, basically error correction capability. And I'd like to kind of overview what we're doing in the HDD, apply an example to what we would see in the basically DNA space, and then show that basically the two are somewhat interchangeable. One of the ways that basically affects basically our soft decoded correction capability is where that decoding threshold is. So I'm going to go through how we would determine that through a concept called mutual information, and then basically provide kind of a quick overview of it, show how we can again apply it to the DNA decoding space, and then kind of try and show again sort of that's application to how you would determine it, and just kind of do a quick summary. So from a recording mechanism perspective for HDDs today, we work on basically magnetic continuous media. So we're flying this basically armature for basically our magnetic write head and read head over our magnetic media. We're using perpendicular magnetic recording today, so we're passing basically a right flux through the media and then basically back out through the right coil. That's basically flipping our magnets basically north and south. Now, I'm not showing energy-assisted magnetic recording. You hear a lot from Seagate on Hammer. That's basically just putting a laser in front of this, heating up the media, and then we're still doing the same thing of basically the normal basically magnetic flux change. Behind that, we're basically passing our reader. So that readback signal is basically quite a noisy signal. It looks quite idealized here today, but what we're sensing is basically the transitions of those north and south magnets. So we're not necessarily sensing, exactly a 1 or a 0 depending on that particular amplitude. It's as that transition happens, that's when we're going to see basically a 1 or a 0 today. So we're dealing with basically the intersymbol interference because our grains aren't basically isolated today. So we have to basically handle the fact within our readback signal and read channel today, sort of this very noisy signal as we get through the particular media. Now the way it's patterned today on the media, obviously we have a rotating technology, so we have to know where we're at on that particular media today. So we write down basically servo index marks, or kind of these servo sectors. That tells us where our positioning is, either from the inner diameter or to the outer diameter. So we have a loop system that we can use our actuator to basically position ourselves anywhere on that particular disk, as well as hold our position down that track so we can write or read. In between each of those, we have our data sectors today. So that's where we're actually storing all that user information. Each data sector is its own LDPC code word. So each data sector down the track basically is its own individual code word. It may have some basically splits or fragments that we have to construct into one code word, but today you can think of each individual data sector for a user is its own individual code word. Now, how we do our particular decoding today, and one of the things we use in one of our recording technologies, which is shingled magnetic recording, is if you want to think about just like Omer showed earlier, we also apply kind of an inner and outer codec scheme. Each individual data sector is its own basically code word, so we have to do our coding, basically decoding for each individual data sector today. But down the track, all the way at the end, we will assemble all these data sectors and pull out parity and also add additional parity sector to the disk, which is in itself its own LDPC code word. So when we go in through our particular decoding today, we have a particular threshold based on our code rate that's targeted for HDDs today. So what we'll see is we might have sectors that are in error that we can't decode on the fly. So what we will use is basically this soft track parity sector to go back and now improve that information for those other words. So you can think about that it's an iterative design in the sense that we'll pass through, read those data sectors basically as we go down the track. If we couldn't do it, we will have already read this data parity sector, and then we can go back and improve those sectors to basically push them up over our decoding threshold, and then basically our overall data sectors for that particular track are recovered. So you can think about that we're using this outer codec to basically supplement our power of our inner codec today, and we can utilize more or less power here depending on how much we want to use for basically additional error recovery, or if we wanted to trade how complex basically our initial LDPC decoder is. Now, if we apply that to a DNA space, I'm going to walk through a particular, let's say, design strategy that you could envision based on DNA. So what we can do is we can take a particular pool of oligos, and we can basically stripe a code word, basically some type of LDPC code word across that. You can construct it in any way and select that. Then you can go back and basically reconstruct another larger block from additional parity, and then basically put that on the end, just like we had before, where you have an additional parity sector that you can use to correct for individual code words failing. So if we apply that very similar concept, the only thing I had to change on this slide is the fact that instead of me saying that's a data sector, now we just have to replace the word with code word. I don't care what went in that code word. It's still the same LDPC code word design. It could be many oligos that are participating in that, but we can still apply the same type of technology. We still define what decoding threshold is going to define if I can actually decode that particular code word. And if it doesn't work, I can now use that sort of super block error correction, basically parity sector that I put out there in order to improve the code words that didn't basically pass, or if they're simply missing, I can reconstruct that. And then at the end, my overall super block that I've protected with that is fully recovered. So again, kind of applying very similar technology that we've already been applying on our HDD products today, we can apply that basically here through DNA storage as well. Now, one of the items they kind of basically just glossed over is what is that decoding threshold? It's obviously very important because where you define that basically defines how much redundancy I'm going to put on each individual code word. So that way, as I pass it through the detector, I know basically whether or not I'm going to be able to decode that. So one of the basically concepts that we use in the HDD space is a concept that's called mutual information. If you actually look it up on the web, some of the things in machine learning today, I think one of the articles one of my engineers found is that they said, well, it's the correlation for the 21st century. Now, whether or not I believe that, I don't know. But the idea is that from mutual information, it basically means what is the relationship between what I wrote and what I read. And it comes from basically information theory, so it basically is a derivation from Claude Shannon's basically information theory as to how it basically passed through. And it's really, that information is how do we resolve the uncertainty in this channel? And it can be described in a number of different ways. And like I said, there's a particular equation that goes behind this, but the idea really is how do we define sort of what that area of uncertainty is, and how do I know if I know what I wrote and what I read, what is that basically decode rate? So I'll provide a little bit of an easier example to maybe consume, which is that we can think about the error correction code is how do we basically pass additional information that's going to aid us in recovery. So if I see that my particular quality of my signal is, let's say, 7 out of 8, And I've encoded 8 out of 8 here because I'm devoting one particular, basically, let's say parity bit here in this particular equation. I read 7 out of the 8. I know I had 8 out of the 8. Therefore, that's going to pass in the channel. I don't need to do any further decoding in terms of actually seeing what the sector failure rate is. I know that the channel is carrying 7 out of the 8% of the information. I already put 1/7 in there to be able to correct anything. Therefore, I know I'm going to be able to reconstruct anything in that particular channel. So it's really a vessel to basically say, how much code rate do I need in order to successfully basically pass my signal through the channel? So it's kind of a faster way without necessarily having to simulate all through the final sector failure rate. You can get this much faster, and you don't actually have to make a decoder to be able to go and verify that. So if we apply this to something like DNA storage, we can define some type of system that has a certain, rate of basically mutation errors, maybe a certain rate of erasure errors, and then we can take some of the more traditional ways of how we would do, let's say, some of the things at the outer codec level. Things like, let's say, Reed-Solomon from a hard basis, since basically Reed-Solomon's basically a hard error correction capability. We can apply it to something like LDPC, and I didn't put all of the equations here for the soft information. If somebody really wants those afterwards, I can provide those as needed. So if we basically run that through, what we'll see is, depending on if I only look at bit errors here on the left, we can now basically generate what's our effective code rate or mutual information for some assumed bit error rate through that particular channel. So there's going to be an obvious functional change as our error rate gets worse and worse here over on the x-axis as to how much additional redundancy am I going to have to employ to be able to correct that. And on the right side, if we look at something like a more of a symbol-based error rate or a larger portion, not just individual bit errors, something like, if we consider just pure erasures in the channel, something like a Reed-Solomon works quite well, where if I have some type of mixture that's more of kind of, let's say, just symbol-based errors, this kind of represents the upper bound and lower bound of where I'm going to need to be in terms of where our mutual information or kind of code rate needs to be in that particular channel. And LDPC can kind of sit somewhere in the middle there, and it's nice that basically it converges all the way up there in the top, and it's just kind of depending on what your channel looks like, you can choose and sort of effectively pick out what type of mutual information or what code rate you would need for that particular system. So in summary, a lot of the techniques that we're already utilizing in sort of that magnetic storage space can already be readily applied, and there's techniques here that I didn't necessarily go through that we're already sort of exploring and utilizing in this particular space. One of those here is, again, kind of the concept of sort of a soft decoded superblock sort of parity correction capability. And again, sort of mutual information can also be applied to DNA storage through basically kind of just defining that relationship between both writes and reads. And again, it's quite a valuable metric because it doesn't basically require you to actually go and simulate all of the sector failure rate or individual bit error rates of your particular channel. You can simply just calculate what that would be, and that makes it much easier in terms of your overall decoder design and evaluation. So that's all I had to discuss today. I'll take any questions. Yes, Stefan.
You showed some data with LDPC. Do you have ideas of how you compare with different error correction types of error correction codes? Did you try other things?
Yeah, we've tried both RS as well as LDPC. I think we've seen that the LDPC design has to be different than the LDPC code construction that we use in the traditional HDD case today, but I think we've found, at least in a working LDPC code, that does seem to work quite well and exhibits very similar properties in terms of error correction that we see on the HDD space. So we can correct quite a few, let's say, missing oligos out of that particular superblock pool quite efficiently as well.
And what about the different error types, meaning the insertion and deletions, which are very different from just substitutions?
Yeah, I think what I maybe glossed over here and you picked up is that, we're solving that more at the intercodec level, so at the level that's basically would define those oligos basically participating in your superblock. I think we've done quite a bit of work developing an intercodec that basically removes all those substitution and deletion errors such that we didn't have to worry about them as much at that outer codec level, just because that follows, I would say, more of the traditional design where the outer codec doesn't have to worry about those errors as well.
Thank you.
Any more questions, comments? Do we have something from our online viewers? Oh. Okay, then in that case, I think we can thank our speaker. Thank you, Austin. One more.